Okay, we'll start now. Okay, so I posted the assignment on Moodle. It's the first assignment that is done in undergraduate operating system. But what is that thing beeping here? Okay, so that assignment, it's an optional assignment, and if you have not done that, so if you have not taken that course here, so if you have not done that assignment, I strongly advise you to do that. Something is beeping here. Isn't it? Oh, okay. Okay. So so try to do that assignment. It's really, if you just follow the steps, don't try to make any changes in the things that are stated there, and you should be able to do that assignment. Okay, it's a really nice experience in terms of finding out what it takes to compile a Linux kernel. Okay, so what that assignment consists of is that you basically first download the source code of Linux kernel, and then make some changes in that. Okay, and then compile it and then run it. So definitely do that. Compilation process can take very long time, depending on the type of machine you have. It can take from half an hour to 3 or 4 hours actually, the actual compilation time. Okay, but try to do that assignment. It's optional, but still I will advise you to do it. Okay, still something beep. So the other thing is, I didn't realize that Monday was a holiday, so we are kind of running one lecture late actually. We are supposed to discuss project today, but we are still doing the reviews. So the dates that I mentioned in our the project handout, we will move all those things by one lecture. Okay, so I'll post the new dates. So next lecture is when we will discuss possible class projects, and your team assignment will be due, team composition will be due, I think it's supposed to be due next Wednesday, so it will be the following Monday. So I'll update all that, all those dates on Moodle. Okay, so what we will do is we'll continue with our discussion on the review of fundamental concepts of operating systems. And in the last class we talked about process management. Today we'll talk about memory management and virtual memory, and then we will move on to discussing secondary storage, disk and flash memory and file system and those kind of things. Okay. So memory management, the main thing about memory management is when we look at this architecture, we have the CPU and you have the main memory, and what memory management basically does is it basically tells you how CPU interacts with main memory. So how do you manage this memory is what memory management is all about. Okay. Now storage, of course, has there is a hierarchy of storage in any computing system. Okay, main memory is only one part of it. Okay, and the way this memory works is typically your code, the program that you compile, it sits on your disk, hard disk. Okay, and so when you want to run that program, okay, the first thing that happens is that this program is loaded into the main memory. Okay, so that's the first thing. And once it has been loaded into the memory, after that there is this fetch and execute cycle between the CPU and the main memory. Okay, so basically the code, each instruction is fetched from the main memory into the CPU, and then the CPU basically writes back into the main memory in the data section or the stack section. Okay, and so basically this cycle continues. Okay, now in the process, CPU also makes use of some other types of memory. So we already seeing the registers here. Okay, there is also L1 cache. L1 cache basically is a very fast memory that sits in the same chip as the where the ALU and the bus interface and all that is. Okay, so that's basically the L1 cache. L2 cache is also there, which is off the chip. Okay, that's where basically L2 cache sits. Okay, some processors have L3 cache, which is basically if you have multiple cores, then some cache are shared by the cores, and then each core may have its own cache. So one is L2 cache, the other is L3 cache. Okay. So this is basically shows you a memory hierarchy. Registers are the fastest memory that is there in a computing system. Then comes L1 cache, then L2 cache, and then basically there comes your main memory. Okay, and after that is the secondary storage, which is the disk. Okay, and so what I showed was basically the ordering in terms of the speed. So registers are the fastest, then L1 cache, then L2 cache, and so on. Okay. However, in terms of cost also, registers are the most expensive piece of memory if you look at per byte cost. Okay. Next is L1 cache, next is L2 cache, then memory, and then disk is one of the cheapest storage device. Okay. So as a result, what happens is in any computing system, you will have lots of secondary storage, you can store a lot of things on the disk, relatively less amount in main memory, typically in few gigabytes. Okay. L2 cache, L1 cache are maybe, typically in kilobytes, sometimes even megabytes, but not beyond that. Registers are only a few registers. Okay. So when a program becomes an active process, okay, then this process can be viewed as conceptually executing in a logical address space ranging from 0 to some max. Okay. So when you compile a program, okay, it is assumed that the program is going to execute in an address space, and the address of those addresses will start from address 0, and it will continue until some max. So every program that you compile, okay, every program, its logical address space starts at address 0, and then it runs at to some maximum. Okay. Now when you start running the program, when you load it into the memory, there is the physical address. So basically these logical addresses, which are from 0 to some max, they have to be now translated into the actual physical address, and the physical addresses you come to know only when you load the program into memory, because depending on where in memory you load your executable, that determines what the actual physical addresses are going to be. Okay, so you have to basically translate those logical addresses into physical address when the program is loaded into the main memory. Okay. So in reality, the code and data, of course, are stored in physical memory. So there needs to be a mapping from logical address space to physical address space. Okay, and this is done by a component of operating system that's called MMU, or Memory Management Unit. Okay, so the job of Memory Management Unit is to take a logical address and produce a corresponding physical address. Okay. So MMU basically does address translation, translate logical address into physical address. Okay. And it also does some bound checking. So it basically makes sure that when it gets a logical address, it will make sure that this logical address that it's looking at actually belongs to this process. That is, it is between 0 and max. Okay. So if an address is outside that range, it's basically what will cause something like segmentation fault in your program. Okay. Now, in order to do this bound checking and this translation, computing architectures provide two registers, special registers. One is base register, and the other is a limit register. Okay. We look at that. We first look at the address binding. That is, when is it that you translate the logical address into a physical address? Okay. So logical address is basically given when you compile the program. Okay. The question is, when do you basically change those logical address into the physical address? Okay. And there are three different times you can do it. The first thing you can do it is in compile time only. That is, when you compile the program, if at that time you know where in memory this program is going to be loaded, okay, then you can basically change all the logical addresses into the physical address, translate them, and so that the program that you store in disk, it will store the physical addresses in that case. So you compile the program and then change all the logical address to physical address. Okay. Now, of course, the key problem there is that when you want to run this program, it must be loaded at that starting address, whatever was given at compile time. Okay. Is that clear? Okay. So that's what is called compile time binding. That is, the address where the program is going to be loaded in memory, it has to be known during compilation, okay, and so that you can hard code all the physical addresses in the executable code itself. Okay. The other option is the load time. Okay. That is, the executable image that is there on the disk, it contains only the logical addresses. Okay. And when you want to actually run the program, at that time the operating system determines that, okay, this is the starting address, this is where I'm going to load this this executable. So at that time you come to know that this is the beginning address of this program. So at that time you basically change the logical address. So before you actually put the code into the memory, you change all the logical address, because at that time you know the starting address in the memory. So that's what is called load time. Okay. And the third thing is basically what is called runtime and execution, or execution time binding. This is where, when you load the program into memory, the image of the program in memory still contains only logical addresses. Okay. When CPU is executing on some instruction, okay, all it sees is logical address. Okay. And whenever the CPU tries to access the memory, the logical address goes through the memory management unit, which converts that, at runtime, it converts that logical address to physical address and then retrieves the data. So the picture for the third, that's the runtime binding, looks something like this. So in RAM, the program that you have stored here, okay, that program contains only logical addresses. Okay. Now, wherever the program has been loaded, the start address is loaded into the base register. Okay. So let's say you load the program is starting at address say 1000. Okay. So that 1000 will be loaded here. Limit basically is what is the max. Okay, so 0 through max. So limit basically tells you max. So when an instruction is loaded from RAM memory into CPU, the instruction still contains only logical address. Okay. Now when CPU wants to get some data from the RAM, okay, it will basically give the logical address to this memory management unit. The MMU will first check the limit, that is, because this is a logical address, so it must be between 0 and max. So that's basically it checks first. Okay. And if it is within the limit, then basically to that logical address it adds the base address or relocation address. Okay. And then out comes a physical address, and this is basically the physical address basically tells you from where in memory that byte has to be retrieved. Is that clear? Okay. This is basically all modern operating systems. They basically do this. Runtime binding, because it gives you a lot of flexibility. Okay. In particular, if you think about a program that's running at some point, and let's say it has run halfway through, and for some reason you want to move that program out of the memory, into the disk, and later on you want to reload that program into memory. Okay. Now, when that happens, it's very unlikely that you will get the same memory space where the program was first loaded. Okay. You'll probably have to load that program at some other place in the memory. So that means the start address will change. Okay. Now, if you are using load time, that will not work, because load time you have already translated your logical address to physical address the first time you loaded the program. Okay. So the runtime basically allows you to do that, the swapping part. Okay. So the swapping is basically a situation where you may be running, say, hundreds of different programs at any point in time, and your memory may not be large enough to hold all those 100 programs that you're running at the same time. Okay. So memory may not be able to store all processes that are ready to run. Okay. So use disk or secondary storage to store some processes that are temporarily swapped out of the memory, so that other processes may execute in memory. So the idea here is that at any point in time, if you have just say one CPU, only one process will be running. Okay. So keep only those processes that are maybe at the head of the ready queue or something, okay, in memory. Rest of them you put in the disk. And then you basically, in the background, you have to keep swapping processes between memory and disk, so that by the time a process is ready to execute and it gets the CPU, its image is already available on memory. Okay. Now, the swapping has to be done very fast. So typically what is done is a special one partition in a disk is reserved for swapping purposes. Okay. And it's called backing store or swap space. And this basically, in order to access that part of the disk, the swap space, you typically don't go through the file system. We'll study file system later on. But file system basically will slow down the access to the disk, because file system has to do all kinds of, run all kinds of algorithm. Okay, so the swapping part actually, circumvents this file system. Now, with runtime binding, as I said, process can be easily swapped back into a different area of the memory. Okay. Now, there are, of course, problem with swapping. And the big problem, of course, is the context switch time of swapping can be very slow. That is, if you want to load a process and if the process is in the disk, okay, then you have to first load that process in the memory and then load that into the CPU. Okay, so the context switch time can be very slow. Okay, so typically operating systems will avoid swapping unless two things actually. One is some operating systems will make sure that a process that is in the disk will not get the CPU. And the second thing is basically operating systems will make sure that they don't swap the processes unless it's absolutely necessary. So we'll look at this in more detail. So now in main memory, as we said, the processes are coming and going, right? So in this case, in this image, we have operating system, of course, which always resides in memory. Okay, and then in addition to that, let's say we have process P1 and P3 that are currently loaded. Okay, so now anytime a new process is loaded, so far when you think about the process, basically when you want to load a process, the entire process has to be loaded in memory, because all you are storing is the starting address of the process, right, which is stored in the base register. Okay, so if you want to, let's say, load a new process, say P2, okay, you want to make sure that there is enough memory available in here to load P2, but not only enough memory is available, but all that memory has to be contiguous. Okay, that is, if you, let's say, start loading the process here, then process P2 must be smaller than this space. Okay, that is, even if the sum of this memory space and this memory space and this memory space might exceed P2 size, but if P2 cannot fit in any of these individual partition, you cannot load P2. Okay, so this is what is called external fragmentation. That is, over time, when you bring in process, take down, load new processes and all, a lot of times what happens is in RAM you will end up with these very small chunks of memory. Okay, where no process will fit. These are so small that no process will fit. These are free memory. However, it cannot be used because processes cannot be loaded over there. Okay, so memory allocation has to be done in such a way that it minimizes this external fragmentation. Okay, so that you don't end up with these small chunks of memory. Yeah.
Why can't you partition a process into separate parts?
Right. So that will come later. Yeah. Right now, we are just talking about the process has to be loaded.
Oh, okay.
Yeah. We will talk about paging later on. Okay. So the memory allocation strategies, there are several. One is best fit, means find the smallest chunk that is big enough. Okay, which is actually a bad idea, because when you find the smallest chunk that is just big enough, that means you will be left with lots of smaller chunks. Okay. The worst fit is find the largest chunk that is big enough. Okay, this is a works good, but the only problem is, in order to find out the worst fit, you have to basically look at all the chunks that are available to decide which one is the largest. Okay. First fit, basically you look through this version, and the first chunk that is large enough, you put it there. Or the next fit is basically you kind of have a circular buffer, so you basically keep a pointer that this is the place you looked at last time. Okay, so the next time you start looking from there onwards, kind of thing. So instead of always looking for the memory from the beginning of the memory, okay, in the next fit you basically start looking from the place where you left off last time. Now, in order to prevent none of these techniques will fully prevent external fragmentation. Okay, so now in order to prevent external fragmentation, what is done is a technique that is used is called paging. Something similar to what he was talking about. Okay, that is, you divide your memory into units of equal size these are what are called memory frames, or frames, simply page frames. Okay, and then you divide your logical address space of the process into units of same size, and these are called pages. Okay, so basically you have a logical address space of the process varying from say 0 to some max number. Let's say your page size is say 4K. Okay, then you will say that the first 4K bytes of this process will sit in page number 0. Okay, the next 4K will sit in page number 1, and then page number 2, and so on. Okay, page frames are same size as page size, so that means you can fit an entire page of logical address space into a single page frame in main memory. Okay, so the allocation of memory to a process is done in terms of now page frames. So you allocate that, okay, for this process I'm going to allocate 10 page frames, kind of thing. Okay. Now, once we do this, now we need a page table to keep track of where each of the page of the process is loaded in memory. So where is page 0 loaded, where is page 1 loaded, where is page 2 loaded, and so on. Okay. We didn't have that problem before because we were putting the entire process contiguously in memory. So all we needed to know is the starting address, which was stored in the base register. Okay. So now what happens is you have the main memory divided into frames, okay, and then you have the logical address space divided into pages, okay, and then you basically maintain a page table. So this page table basically says that page number 0 of this process is loaded in physical frame number 1, page number 1 is loaded in page frame number 4, 2 is loaded in page frame number 3, and so on. Okay. And some of the page frames are currently unallocated, and so if a new process comes in, and in this case, as long as that process needs less than or equal to 3 page frames, it can basically, that process also can be allocated here. Okay. These 3 page frames can be allocated to that new process. Okay. So conceptually, every logical address can be divided into 2 parts. So the thing is that now, given a logical address, you have to do 2 things. One is, you have to first, given a logical address, you have to figure out which page this address belongs to. Okay? And that's basically dividing this logical address by the page size. Okay? And the second thing is, once you find the page, what is the offset within the page, for that logical address. Okay? So you have to figure out the page number and the offset. Yeah.
These page tables are a part of process descriptors, or
they will be a part of the process descriptor. That's correct. Okay. Okay. So now this is where, when you decide what page sizes you are going to use, okay, you basically use a number which is a power of 2. Okay, because when you use a number which is a power of 2, when you divide something by a power of 2, all it is basically shifts. Left shifts or right shift. Multiplying is left shift, and dividing is right shift. Okay, or other way to say that is, let's say you decide that there are d bits, that you choose to represent page sizes. So for example, if you have a page size of 1K, that means you will need 10 bits to represent represent all the addresses within a page. Okay, so that's basically the lower order 10 bits. That's your page. These depends on the page size. The remaining bits basically tell you the page number. Okay, so given a logical address, all you have to do is basically look at the first few bits here, which will give you the page number. Okay, now take that page number and index into the page table. That will give you the frame number. Okay, and then you take the offset here, and you basically put that offset into this, and this basically gives you the physical address. Is that clear? Okay. So it's basically, you can do this very fast. You can do this because you're choosing pages which are powers of 2. Okay. Now, this translation, that is, looking at a logical address, going to the page table, and then doing this offset thing, and then finding the actual frame number and all, this is something that you have to do on every memory access. And if you recall some of the instructions on modern computing systems, they can actually result in something like 2 or 3 or sometimes even 4 memory accesses. Okay, so to execute a single instruction may require something like 3 or 4 memory access, which means it will require 3 or 4 times you have to do this process of going through the page table and doing the translation. Okay. Which means that you really want to do this mapping from logical address to physical address through paging very fast. Okay. And so in order to do that, all computing architectures, they provide CPU buffers, which are basically caches. So in the CPU that we saw registers and L1 cache. There is also another cache, which is what is called translation look-aside buffers, or TLBs. Okay. And TLBs are basically provided so that you can do this mapping from logical address to physical address using page tables very fast. Okay. So TLBs are implemented in the hardware, and they basically allow you to do a parallel search. So you can imagine TLBs as simply as tables, right? So one column the table is page number, the other column the page is the frame number. Okay. So you have like several rows. Okay. And in hardware, given a page number, you do a parallel search and you get hit. Okay. And so that search is very, very fast. Okay. So this is how basically this will work. So in the CPU, you have this TLB, okay, and this is where you basically store that page table. But the TLB, the size of the TLB is limited because this is cache, okay. So only a few page and a few entries you'll be able to store here. Okay, and given a logical address, you take this the first few bytes and then search into this in parallel. So this is all is done in hardware. Okay, so you do a parallel search, and if you get a hit, okay, then pick up the corresponding frame number and then put that frame number here. Yeah.
So the look-aside buffer, is it essentially like a small subset of the actual page table that is stored? Which
yeah. That's right. So there are strategies of which entries to keep in the look-aside buffer. So I'm not going to go into that, but yes, there are strategies. Which page. Basically, you have to estimate. Which pages you are likely to access, and those are the ones that you will keep in TLBs. Okay. So, and if you get a hit, you basically do that. However, you can get a miss, which means that you do the parallel search, but you don't find the entry here in the page. Okay. In that case, what you have to do is there is a register. It's called PTBR, page table base register. Okay. And what page table base register basically stores is the address of the page table in memory. So the process that's running, its page table is stored in memory, and part of this page table is over here. Okay, but in this case, what has happened is that you haven't gotten a hit. So what you basically go to the page table base register, and from there you basically find the frame, because that page table, of course, will have the corresponding entry. So you kind of find the frame. You put the frame over here. Okay, but this is where now, since this is the page table, and we'll talk about this, there is this principle of locality of reference. Okay. What it says is that if you access a page recently, there is a very high likelihood that you will access that page again. Okay. So, which means that if you have accessed this page, which caused this miss, okay, it's very likely that you are going to access this page again. So it's a good idea to move this page page entry into the TLB, so that next time you're going to access it, you will not get a miss. Because as you can imagine, when you have a miss, you have to look into this, and then you have to go to the memory, get the page frame number. So it's basically a overhead. Okay, so you want to avoid that overhead. Okay. So the next thing that you do is you basically update your TLB. You bring that entry into here, and when you bring that, you may have to to overwrite one of the entry that's already over there. And so there are many strategies. You might want to take out the entry that you have not used for the longest period of time. That's the one that you might want to overwrite with. Okay. Any questions about that? Now, the problem with page tables is that these page tables can get very large. Okay. So, and notice that although we said that the pages, the pages in memory, pages of a particular process, they can be stored anywhere in memory, in any frame, right? However, if you think about the page table, okay, that is there in memory, the page table has to be stored contiguously, because all you have is a page table base register, which tells you where the page table is stored in the beginning address. So the entire page table has to be stored contiguously. Okay. Now, if your page table is large, okay, then, and if you are running lots of processes, then these page tables can actually end up occupying lots of memory themselves. Okay. So the next step is basically what is called hierarchical paging. Okay. So instead of maintaining a single page table, okay, which gives you a direct translation from page number to frame number, okay, you can basically make a two-level page table. So the first page table provides an index to a next page table, and that next page table will give you the actual translation of the page number to the frame number. Okay. So that will be a two-level page table. So this is an example of a two-level page table. That is, there is an outer page table. Okay. So given a logical address, it basically gives you a pointer to a page table. So there are several secondary level page tables. Okay. So basically it gives you the pointer to one of the page table, and then there you again index into it and then find the right frame. Okay. So now basically the mapping is done 2 times. Okay. So when you have a 2-level page table, you basically divide your logical address space into 3 parts now. Okay. The first few bits will index into the outer page table. Okay. And then they will basically give you the frame number where the secondary page table is stored, which contains the address that you are looking for. Okay. So that basically provides you the index into the secondary page table, and then secondary page table you basically take this address and then index into it, and that gives you the frame number, and then you get the displacement over here. Is that clear? Yeah.
But aren't all the page tables still being stored in the RAM? I mean, it's
Right. But notice that the secondary page tables, now each of these individual page tables don't have to stay to be stored consecutively. Okay. So all you have to know is the address of the outer page table. So your page table register will store here. Okay. Others basically their addresses you are storing in the page table, outer page table. So now your page table can be scattered all over the memory.
Okay, so this is not to reduce the memory. This is basically to stop it from.
Right. That's right. Okay. Any other question? Okay. Now, hierarchical page tables do not solve the problem of large table size, because you still have to store all the page tables. Okay. And so this is where the idea of inverted page table comes in. Okay. What inverted page table does is, instead of storing the mapping from page number to frame number, okay, what inverted page table does is it basically stores the mapping from frame number to the page number. But now that mapping is not sufficient, because when you see a frame number and page number, you have to figure out which process this page belongs to. So now you have to store 2 entries. Okay? Frame number maps to a page number and the process ID of that page. Who owns that page? Okay? So in a picture, I think I will be, yeah, there I have a picture here. So a logical, in an inverted page table, basically what will happen is you are given a logical address. Okay. The first thing that you do is, in the inverted page table, you have to search throughout the page table. Okay. Look for the, so the logical address now comes with the process ID. Okay, the process ID, and then this is the page number, and this is the displacement. Okay. In the inverted page table, you are storing the entries process ID and the page number, and the third entry I have not shown here, which is basically your frame number. So now you have to basically search through this entire inverted page table and then match these PID and P, and once you get that mapping, then you get the frame number. That's the frame. Is that clear? So, but the main drawback of inverted page table is that when you are doing the search, you have to basically look at the entire inverted page table. So you cannot, if you remember in the previous case, you had a page number and you could directly index into the page table, right? Because that bits basically provided the index. Okay. In this case, you don't have that index anymore. Okay. Now, the advantage is that the size of the page table that you have to store in memory is simply depends on the number of frames you have, right? Because it basically tells you what's stored in the first frame, second frame, third frame, and so on. Is that clear? that's basically the trade-off, of using inverted page table versus the regular page table. Okay, it ensures that you don't have to have you don't have to devote a lot of memory for page tables. Okay, but then you have to search through the entire inverted page table now. Any questions? Okay. Now, the next, so far what we have been able to do is we have been able to do the runtime address binding, okay, so that your processes, your process image always contains logical addresses. The actual physical address is determined only at runtime when you actually need that location, that data or code. Okay. And the second thing that we have seen is that you don't have to store the entire program contiguously in memory. Okay, you can basically scatter that by using paging. Okay. Now, the next thing that comes is all processes in ready queue may not fit in memory. Okay, and so here is a key observation, that is, not all pages in logical address space need to be kept in memory. And this is basically when you have a very large program. Okay, you are really executing only on some part of that program. Okay, so there is really no need to keep the entire program in memory. So the idea here with on-demand paging is you keep only a subset of processes pages in memory. Okay, and then of course the key question is which pages to keep in memory. So this is where this principle of locality of reference comes in, okay, which basically is an empirical observation, which says basically that if an instruction or data references in a page was recently referenced, so if you have looked at a page very recently, okay, then the page is likely to be referenced again in near future. Okay, and the intuition is pretty clear here. Majority of the programs that we write, they are typically sequential in nature. You access a instruction, that next instruction, and that next instruction, and so on. Okay, or let's say you are operating on an array. So you operate on the first element of the array, then the second element of the array, third element of the array. The entire array probably will be stored contiguously in one of the pages. Okay, so that's basically the intuition behind this. And what this basically allows you to do is it basically allows you to make a prediction that if I have looked at this page, okay, most likely I'm going to look at this page again. Okay, so it's a good idea that I keep this page, but not only this page, but also the pages that are near it. So if I'm keeping page number 5, I should also maybe keep page number 6, and maybe even keep page number 4 in case there is a loop or something. Okay. So the idea here is that looping through, so that's basically the principle of locality of reference, and that's basically used along with your paging. Okay, and this basically gives rise to what is called virtual memory. Okay. The advantage of keeping only a subset of each process's pages in RAM instead of the entire logical address space. Okay, so now you can fit many more processes in memory because you don't have to keep the entire process, each of those entire process in memory. Okay. This decreases the swap time because if you have to swap this process out, you have to swap out only a few pages because not entire process is there in memory. Okay. And the logical address space of a process can now exceed the physical RAM. Okay, because at no time you really have to load the entire process in memory. So your memory actually may be say 2 gigabytes, but your process actually might be say 5 gigabytes. Okay, and you will still be able to work as long as you can store those 5 gigabytes in your disk. Okay, is that clear? So this is basically what has happened now here is that you have decoupled this your virtual memory or the logical memory that we are talking about completely from your physical memory. Okay, this is the nice thing about virtual memory, that is when you are writing a program, you really don't have to think about physical memory at all. Okay. Now, when you don't keep the entire process in memory, you have this problem of what is called page fault. Okay. Because when you're running a process, not all pages of that processes are in memory, and suppose in your program you make a jump. Okay, so you're on some page, you're operating on page number 5, and there is an instruction that jumps, and the jump instruction, the target is say on page number 37. Okay, so suddenly you're moving from page number 5 to 37. Okay, it's quite likely that page number 37 is not there in memory. Okay, so this is what is called a page fault. So now, in order to implement virtual memory, what you need as part of your operating system, you need what is called page fault handler, okay, whose job is basically whenever a page fault occurs, okay, to basically load a new page which has been referenced into the memory. Okay. So the page fault handler basically checks if the reference page is not in the logical address space, then it's a segmentation fault. So this is basically if the address is outside your logical address space. Okay. Otherwise, you want to load the page. Okay. So the operating system will find a free frame, a frame that's available, and then it will schedule a disk read. Other processes may run in the meantime. And then the disk basically returns with an interrupt when done reading the desired page. OS writes the page into the free frame. Okay. And so that's basically what a page fault handler does. Is that clear? Now, as you can imagine, page faults are bad because anytime there is a page fault, you have to basically move things from disk to memory definitely, and also if all your frames are filled, then you have to move a page out of the memory into the disk. So, and access to the secondary storage is very slow. Okay, so page faults basically result in significant performance overhead. Okay, so you want to design your memory system such that the number or frequency of page faults is relatively low. Okay, and this basically gives you some idea, So for example, disk read is of the order of 10 milliseconds. A memory read is something like 10 nanoseconds, the order of 10 nanoseconds. Okay, so if you do some calculations, the average access time, if P is the rate of page fault, okay, then your average access time will be P times 10 plus 1 minus P times 10 nanoseconds. Right, that will be the average access time. Okay, and if you think about that, P is say 0.000001. Okay, that means the probability that you are going to encounter a page fault is 1 in 1,000. Okay, that's fairly low, 0.001. But if you do this calculation, you will see that your average access time is 10 microseconds. Okay, compare that with 10 nanoseconds. Okay, you will see that even though your page fault probability is so low, like 0.001, okay, still your access time is increased by 1,000 times. Okay. So the page fault actually has a significant impact on the performance of your system, of your overall system. Okay. So thus, any extra bit of effort to reduce page fault frequency can result in big performance gains. So this is where now the page replacement policy comes in, because what you want to do is make sure that the page that is likely to be referenced next is already there in memory, so that you don't suffer from page faults. Okay. So as processes execute and bring in more pages on demand into memory, eventually the system runs out of free page frames. And so you need a page replacement policy. That is, a page fault, let's say a page fault has occurred. Now what you have to do is you have to overwrite one of the frames. Which one should you overwrite? Okay, that's basically how you need to decide which one to replace now, which page to replace. Okay. And so this is where basically some of the strategies that are used. One thing that is there is that if you have to move a page out of the memory into the disk, okay, you look at the page. Now, if the page that was loaded from disk to the memory, if that page hasn't been modified, so for example, let's say this page contained only code, okay, so that page hasn't been modified. So if you have to replace this page, there is no need to write this page back into the memory. Okay, so this is where the what is called a dirty bit that is provided by the architecture, which basically tells you whether the page is stored in a page frame, whether it's a dirty or not. Okay. Dirty means that somewhat, after the page was loaded, some changes have occurred to it. Okay, and if it is 0, that means no changes have occurred. Okay, so the dirty bit or the modify bit is basically 0 initially. When a page in memory is written to, set the bit to 1. Okay. So now basically you can choose which page to replace you can basically put some more intelligence into it, okay? Because you know that if the dirty bit is 0, you don't have to write the page back, okay? So that becomes your preference, because that will reduce the overhead, okay? So when a victim page is needed, you basically choose a page whose dirty bit is 0. Is that clear? In general, your page table, it actually stores lots of other bits actually. So there is a read-write bit or the read-only bit, which basically tells you whether that page can be written or not, okay? There is a valid or invalid bit, which basically tells you whether a particular page frame, whether a particular entry in the page table is valid or not, okay? So if it is not valid, that means that page is not loaded in memory. Okay? And then the dirty bit that we just talked about, that the page has been modified after it was loaded in memory. Okay? Now, which page does operating system choose to replace? Okay? The policy, assume that the policy is to choose to replace a clean page before a dirty page to save on disk write. Okay, so that's basically one. Okay. Now, with that policy, you may still have several pages whose dirty bits are 0. Okay. So now again, you have to choose which ones to, among those, which ones to replace. And there are many different policies. FIFO is, you can imagine, basically you keep track of which page was brought earliest into the memory. That's the one you replace, kind of thing. Okay. FIFO is not a good policy. It basically suffers from something called Bilardi's anomaly. Okay. And what Bilardi's anomaly says is that one way to decrease the number of page faults or frequency of the page faults is by adding more memory. Because if you have more memory, you can store more pages. Okay. And so that should result in reducing the page faults. Okay. However, if you are using a page replacement policy like FIFO, okay, it can be shown that the number of page faults for a particular program with a given memory, the number of page faults might increase if you increase the size of the memory. Okay, that's basically what is called Bilardi's anomaly. Not a good thing. So FIFO is not a good algorithm. Okay. Optimal is basically an algorithm which assumes that you already know the sequence of pages that you are going to access. Okay. So in advance, you know that, I'm going to access page number 5, then 7, and 3, and 2. You have that string in front of you. Okay. So you have the perfect knowledge there. So you can do the best there, because you can basically look at it and then you can decide, which pages to be there in the memory, because you can look at the string in the future and you know that these are the pages I'm going to need, so I'll keep these pages in memory. This is the page I don't need, so I'll move it out of the memory. Okay. So that's basically what is optimal. And optimal, by definition, will give you the best possible performance. Okay. It will give you the lowest page fault frequency, because you know everything there. Okay. However, very rarely you know actually what pages you are, in advance you know what pages you're going to access. Okay. So optimal is basically gives you a baseline. Okay. It basically tells you, what is the best you could do. So you could, let's say you design 10 different page replacement algorithms. Okay. You know that your goal is to come as close to the performance of optimal as possible, because you know that you cannot do better than optimal. Optimal is the best possible algorithm. So optimal, the usefulness of optimal algorithm is simply to do this evaluation of your page replacement algorithms. Okay. Now LRU is what is called least recently used. Okay. And this is based on this principle of locality of reference. So let me go to there. This is based on principle of locality of reference, which is that if you have looked at a page recently, you are more likely to look at that page again. Okay. So let's say for your process, you have and right now there are 10 different page frames here, and you want to choose a frame that you want to replace. Okay. Then you choose among those 10, look at when was the last time each of those pages were accessed, and then choose the frame that was not least recently used. Okay. It's different from FIFO. FIFO is basically depends on when the page arrived into the memory, while this is looking at when the page was accessed. Okay. So LRU is basically, it can be shown that it's not subject to Bilardi's anomaly. That is, if you increase the size of the memory, your page fault frequency will not increase. Okay. However, the problem with LRU is that the implementation can be complicated and it could be slow, because you have to keep track of all the access times and things like that. Every time to replace, you have to look at all the times and so on.
Yeah, I guess how would it have kept track of the least recently used?
Right. So in theory, basically, you could imagine that you have for each page, you are storing maybe a timer, right? So every time you access the page, you update the time with the current time, right? So, and then when you have to replace, look at all the times, find the one that is the oldest. Okay. So that would be LRU. The problem is that it's very expensive, because you have to do all this time, and more importantly, when you have to replace the page, you have to look at all the timestamps to find which one is the smallest. Okay. So the implementation is complicated. So because of that, most operating systems will implement something which is an approximation of LRU. Okay. Because implementing LRU is can be expensive. Okay. Now, in order to implement approximate LRU, there is an additional hardware bit that is provided, okay, and that is called a reference bit. Okay. So it's a single bit, and all it tells you is whether a page was referenced or not. Okay. So that's all it is. So 0 basically means that the page hasn't been referenced. 1 means page has been referenced. Okay. Notice that reference bit is different from modify bit. Modify bit basically tells you that the page was returned to. Okay. While reference bit is simply it is accessed. So even if you are reading something, that page reference bit will be set. Okay. So this is a set. So basically, what happens now is so the approximate LRU, they use this this reference bit, okay, and there are 3 different types of approximate LRU algorithms. One is called additional second reference bit algorithm, second chance algorithm, and then enhanced clock algorithm. Okay. Let's look at the first one. So in the case of this additional reference bit algorithm, what you do is you basically record the reference bits. Okay. So the idea is that whenever a page is referenced, okay, you set the reference bit to 1. Okay. Now you also maintain maybe a byte. So basically, you record of the last 8 reference bits. Okay. Now, periodically, a timer interrupt shifts right the bits in the record and puts the reference bit into the most significant bit. Okay. So you basically, in the beginning, everything is 0. Your record is 0. All the bits are 0. Okay. And every few nanoseconds, this bit will be right shifted. Okay. And in the most significant bit, you look at the reference bit, whatever the value is, whether it's 0 or 1, you put it as the most significant bit. Okay. So you keep doing that, and whenever there is a page fault, you basically look at these values. Okay. And then LRU, basically you choose the one with the lowest record. So look at these reference bits, which is maybe a byte. Okay. Look at that byte for all the page frames, and look at the one that has the lowest value. Yeah.
When is the reference bit cleared? Because once the reference bit is set, it should be set all through.
No. Okay. So whenever you basically shift your record right, at that time you set the reference bit back to 0. Okay. So every time you're shifting the record right, you put the reference bit in the most significant bit and set the reference bit to 0. Okay. Any other question? So that's basically the approximation of LRU, because it doesn't really guarantee that you are always choosing the page that is least recently used. Okay. But more likely you will be using the one that's most recently used. The second chance algorithm is again, it also uses the reference bit, and all it is basically it organizes all page frames in a logical circle. So page frame number 0, 1, 2, 3, all the way to maybe 7, and followed by 0. Okay. And then you can imagine a pointer. The reason it's called a clock is because the pointer is like a clock hand. So it basically points to one of the frames in this logical circle. Okay. And when there is a page fault, you look at that frame that's pointed to by this pointer. Okay. And look at the reference bit. If the reference bit of that page is 0, you just replace that page. That's the page you choose. Okay. If the reference bit is 1, okay, then you change the reference bit to 0, you move forward and look at the next page. Okay. So that's basically what clock algorithm is. Okay. Basically the main advantage of second chance, it's not as accurate as your approximatal or the previous algorithm that we looked at, additional reference bit algorithm. It's not as accurate as this, but it's very easy to implement. Okay, because if page fault, all you have to look at is the page that's pointed to by this pointer, okay, and look at the reference bit. If not, move forward. In the worst case, you may have to go through the entire circle. Okay. The third one is what is called enhanced second chance algorithm, which not only looks at reference bit, but it also looks at the modified bit. So it basically looks at 2 bits now. Okay, and so basically it looks at it, and then it basically finds that your bit pattern could be either 0 0 or 0 0 1 or 1 0 or 1 1. Okay, 0 0 is clearly the least heavily used class, right? Because it hasn't been referenced recently and it hasn't been modified recently. Okay, so this is definitely the preference, the one that you want to choose. Okay, if there is no page that belongs to this category, then you basically go to this page where the modified bit is 1 and the reference bit is 0. Okay, now this is actually a little bit. Remember that reference bit. Our initial policy was that you will not choose a modified page to replace because you have to write that page back to the memory. However, here you actually give preference to one which has a modified bit 1, and the reason being that an R0 basically, because you are resetting this R bit again and again, R equals 0 basically says that you haven't looked at this page recently, while R1 basically means that you have referenced this page very recently. Okay. The modified bit could have been set much earlier in time because modified bit doesn't change. Once it is set to 1, it remains 1. Okay. So this is the reason you basically give preference to 0 1 pattern here over 1 0 pattern. Okay. Is that clear? The reasoning there? Okay. The next thing is we have been saying that you don't have to keep all pages of a process in memory. Only some pages you have to keep in memory. So the next question is, how many pages should you keep in memory for each process? Okay. And this is where this trade-off comes into play. Okay, and that is basically more processes you keep in memory. That means you have a higher degree of multiprogramming, because you are running lots of processes at the same time. Okay. However, and the result of that is when you increase the degree of multiprogramming, you are increasing CPU utilization because you have more processes to run. So anytime the CPU is available, you will be able to find a process ready to run. Okay. So as you increase the degree of multiprogramming, you will increase the CPU utilization. Okay. However, the other thing that happens is when you increase the degree of multiprogramming, okay, the number of frames that you can allocate to a process is going to be lower. Which means that you will be increasing the page fault rate. Okay. Now, page fault rate basically means that you will be doing this swapping and things like that, which will actually decrease CPU utilization. Okay. So there is this trade-off now. Okay. And typically, when you look at a picture like this, so if you look at a picture of like this, and let's say you have this is where you put, say, a degree of multiprogramming. That is how many processes you are running at a time. Okay, and then this is basically where you plot CPU utilization. Okay, then you will see that in the beginning, as you increase the degree of multiprogramming, you will see a rise in the CPU utilization. Okay, however, at some point it reaches a maximum. And if you increase the degree of multiprogramming beyond that, it basically falls like that. Okay. And so what you want to do is you want to maintain your degree of multiprogramming somewhere around here. Okay, where basically you are maximizing the CPU utilization. Okay? So this is basically a sweet spot where you have the sufficient number of processes in memory, so that you are always able to find a process to run. Okay? But at the same time, you are able to allocate enough number of pages to each process so that your page fault frequency is not very high. Okay? Now, this area is what is called thrashing. Okay? This area is called thrashing. Okay? Now, the problem that happens here is that this point that we are looking at, that peak that we are looking at, okay, it actually depends on the type of program you are running. Okay? So imagine that you have written a program, and that program is very weirdly written. So it basically is making all kinds of jumps in the program, all over the place. It's not like, you haven't followed the nice programming practices there. Okay? If you run that program, what will happen is that it's not going to follow your principle of locality of reference, okay? Which means that it will result in lots of page faults. Okay? Now, if you want to keep the number of page faults below some threshold for this program, you have to allocate lots of memory to this process, lots of frames to this process. Okay? Now, if you allocate lots of frames to this process, that means you can run only a fewer number of other processes. Okay? So what I'm trying to say here is that if all your programs are very nicely behaved, okay, then this point here will be way over here. Okay, so it's basically, if you have lots of good programs, let me actually use a different color to explain this. So if you have lots of very good programs running, very nicely structured programs, you will have something, a picture like that. Okay, where your degree of the peak that you reach is at a very high degree of multiprogramming. But if you have programs are not very well written, or even if there are only a few programs that are misbehaving, okay, your peak will be like way over here. Okay, so that's basically dependent on the type of programs you're running. So it's not something that you can fix in advance. Okay, you have to determine this point during runtime. So you have to basically observe the behavior of your system and then decide, well, at this time, based on the behavior, okay, I should increase the degree of multiprogramming or I should decrease the degree of multiprogramming. Is that clear? So this is where the idea of working set comes into play. Okay, which basically says, decides, for each process, how many frames should you allocate. Okay, and if your memory is not large enough, or if at present you don't have so many available frames at this point, you won't run this process. Okay, so you basically allocate a minimum number of frames for each process, and that number actually will vary depending on the process. So a nicely behaved process will have that a smaller number, while a badly behaving process will have that number to be a larger number. Okay, so the way this is done is you determine, you basically look at, you basically set a threshold that you are going to tolerate for each process. You are going to tolerate, only so many page faults per unit time. Okay, and then basically observe, if you see that the number of page faults for this particular processor is increasing in the last, some tau, time units, you see that the number of page faults are actually larger than whatever your threshold was, you allocate an extra page frame to this process. Okay, if you don't have an extra page frame, move that process out of the memory. Okay, so what working set basically is, the working set is basically the set of pages you need to keep in memory before you can actually run that process. Okay, so if you have to decide that for a particular process to run, you need to keep at least 4 pages. If you don't have 4 pages in memory, you don't run that process. So, so this T is adjusted, dynamically, and you can read through it. But the basic idea is that a process will run only if its working set is in memory. Okay? If the working set is not in memory, that is, if there is a process, working set size is, say, for that particular process, say 5, you don't have 5 frames for this process, you don't run that process. Is that clear? So that's basically everything about memory management. A few system calls that you should be aware of for managing memory. There is a system called a break, which basically sets the end of the data segment, which is at the end of the heap. Okay, and then there is mmap, which basically maps data segments to various files and so on. Okay, sbreak basically adds a displacement. Okay, so both this break and sbreak, they will extend the size of your heap in your program. Okay, mmac basically creates new mapping in the virtual address space for the calling process. Okay. Typically, when we write programs like C, whenever we need more memory, we will use a library called malloc. Okay, and what malloc does is it basically makes this system call sbreak. Okay, you can do sbreak. You can directly make this call. It's not advisable, and the reason it's not advisable is because malloc actually does a very smart way to ask for the space. So, for example, whenever you need memory, let's say you need memory for, say, I don't know, 1 kilobyte. What malloc will do is it will call sbreak, but it will may obtain 4 kilobytes. Okay, and the idea is that next time when you need more memory calling through malloc, okay, it will basically choose the memory, so it doesn't have to call sbreak again. Okay, because system calls are expensive. Okay, so malloc actually does buffering. So you needed 1 kilobyte, it got 4 kilobytes, the 3 kilobytes it is keeping in its buffer. Next time you need more memory, it will allocate from its buffer instead of calling sbreak. Okay. So malloc is actually much more efficient, so you should always use malloc instead of sbreak. Okay. There are some other calls for virtual memory. You can get basically some configuration parameters like what is the page size of your system. You can have get page size in your program to guide the page size of the system, and other things like some limits and things like that. Okay. Any questions about memory and virtual memory?
So what about the segmentation? Sometimes
Right. So I did not talk about segmentation actually. So we talked about paging, that is dividing logical address into fixed size pages. Okay. The downside of paging is that it's basically dependent strictly on the page size. Okay. Ideally, what you would like is when you want to break your program, process into multiple units, each unit should be a complete logical unit. So, for example, a unit may contain 5 different functions completely. Okay, so that you don't want to have a page boundary that breaks, that's somewhere in between a function. Because that would naturally, when you are executing, it will result in page faults. Okay, so there is another technique. It's called segmentation. The segmentation basically breaks the logical address space of the process into logical units. So basically there will be one unit for, say, 5 different functions, another unit for maybe the data and things like that. Okay, and some operating systems do implement segmentation, but typically, for efficiency reasons, what happens is that each segment that we looked at, it is then further divided into pages actually. So basically, it's typically what is used is segmentation along with paging to improve the performance. Any other question?
Can we go over mmap again? I didn't really get what that does.
The mmap is basically you have the virtual memory of a process, right? Okay. And let's say you want to say, an example would be, let's say you want to read a file. Okay. Now the file is in the disk, right? You open the file. Okay. What you can do is actually make a copy of that file in your virtual address space. Okay. So that when you're reading that file, you don't have to go to the secondary storage anymore. Basically, access to the file now is basically just accessing the address in your virtual memory. So to do that, you will use something like mmap. Okay, mapping.
So you map the memory of the text file to somewhere in the
Correct.
program.
Correct.
Okay.
Okay. Any other question? So that's. Let me quickly start with the third set of slides. Okay, which talks about secondary storage. We'll just take a few minutes here. So we've looked at the CPU, which is basically all process management, and we looked at main memory. That was memory management. Okay. The third important component in a computing system is your secondary storage. Okay. And that's basically where what we will talk about, which is secondary storage and a file system which makes use of secondary storage for managing the, the secondary storage. And then we'll talk about security and protection. Okay. So the most common secondary storage that we use today right now is magnetic disk. And although there are, flash drives are becoming more and more popular, okay, still the popular technology for hard disk is still magnetic disks. Okay. A magnetic disk, basically, the structure of a magnetic disk looks something like this. It consists of several plates like this, okay, and then you have an arm assembly like this, and then you have an arm that basically floats over each of these platters. Okay, so and then you can basically, each of this platter is divided into concentric circles, and those are basically what are called tracks. Okay, so basically each of this is divided into tracks, and then each track is divided into sectors. So you can take a track and then divide each track into sectors. Okay, so whenever you want to access some data in secondary storage, the ultimate address that needs to be given to the disk has to do with, you have to provide the track number, okay, and the sector number, and then the offset within the sector number. Okay, those are the three things you will have to provide. Okay, so whenever you want to basically read or write from the disk, okay, the first thing that you have to do is you have to move this arm to the right track. Okay, that's the first thing. Okay, move the arm to the right track. Once you have gotten to the right track, you have to wait, because each of these platter, this is spinning. Okay, so now once you have come on top of the right track, now you have to wait for the sector to roll under the arm. Okay, and once that sector comes under the arm, then you can basically start reading that sector. So if you think about the overall latency, disk access latency, there are three parts to it. There is a seek time. Seek time is basically moving the arm to the right track. That's the seek time. Okay. The second thing is what is called rotational latency, which is basically waiting until the right bytes that you want to write sector comes under the arm. And then third thing is the transfer time, which is actually the transfer of the bits or bytes from the disk to the device. Okay, so those are the three parts of disk latency. Disk time is typically about 5 to 10 milliseconds. Seek time, sorry. Rotational latency can vary from 1 to 5 milliseconds. Transfer time is in microseconds. Okay. So as you can see, if you want to optimize, minimize your latency, you have to really work on these two things. You want to minimize seek time, you want to minimize rotational latency, because this is very small, so you don't have to worry too much about it. Is that clear? So disk scheduling has to do with minimizing the seek time. Okay. That is, how do you make sure that your seek time, that is time to get the arm on top of the right track, is lowered. And the idea here is that at any point in time, the operating system will have a sequence of tracks from which it needs to read. Okay. So it will say, okay, I want to read from track number 15, after that track number 17, and then track number 32, and that kind of thing. Okay. So there are different types of scheduling. First is what is called FCFS, first come first serve, which is basically if the sequence is let me write a sequence here, just if the sequence is say 10, 7, 18, 0, 27, like that. Okay, then first come first serve will basically go to track number 10, then track number 7, then track number 18, then track number 0, and then track number 27. Okay, so you can see the amount of distance that the arm has to travel. So from 10 to 7, it has to travel a distance of 3. From 7 to 18, it has to travel a distance of 11. Here it has to travel a distance of 18. Here it has to travel a distance of 27. Okay. Now the distance basically translates to a seek time. Okay. More the distance, more will be the seek time. Okay. So what you want to do is you want to basically minimize this, average value of that you want to minimize. So in case of FCFS, this is what your total seek time will be. You just add them up. Okay. Another technique that is used is what is called shortest seek time first. Okay, so basically, given where the position you are in, you look at all the other sectors that you need, tracks you need to go to, and find the one that is closest to it. Okay, and then go to that. So, for example, if you are, let's say, on 7, you already gone through say, sorry, let's say you start. Suppose at this point you are at track number say 8. Okay, now these are the tracks you have to go to. Well, you immediately see that 7 is the closest from 8, so that's the first one you go to. Okay, once you are on 7, you will see that the closest one after 7 is going to be 10, so you go to 10. Okay, once you are on 10, you will see that the one that is closest is actually 0 from 10, so you go to 0. Then from 0, basically 18 will be the next, and then 27 will be the next. Okay, so it's basically you're looking to minimize the seek time, the next seek time. Okay, it's not optimal, but the bigger problem with SSTF is subject to starvation. That is, if you have, if you can imagine that you have a lot of these concentric disks. Okay, what happens with SSTF is most of the time you kind of do these things. The tracks that are on the outer edges, either here or here, they actually suffer. So they get starved. Because you can imagine in order to go to those outer edges, your seek time is going to be larger. So most of the time you will find that in order to go to the outer edges, the distance is going to be longer than one of the other sector, that's one of the other track you have to go to. Okay. The next one is what is called scan or look scheduling. Okay, and this is basically something similar to how elevator works. Okay, that is, you are moving the arm in one direction. Okay, and then as you are moving the arm, you are basically servicing every track that you need to service. Okay, you go all the way to the end, okay, and then you move back. Okay, so that's basically what this scan is. Okay, and again, the scan algorithm is unfair to the tracks that are on the edges, because you go all the way to say track number 100. 0 is very far, so it will take a long time to come back to 0, because you will be servicing every track that is in between as you're coming towards 0. Okay, what C-scan or look does is it basically logically it arranges all your tracks in a circle. So basically it goes from 0 to all the way to 100. Let's say 100 is outermost, goes from 0 to 100, and after 100 it basically comes back to 0. So in case of this elevator analogy, what will happen is you'll go from floor number 0 to floor number 8. After that, you'll come back all the way to floor number 0, and then start servicing again. Okay, that's basically what C-scan is. Most of the systems will implement one of these two. So that's basically disk. Okay, nowadays flash memory is also becoming very popular. Okay, and the flash memory, unlike magnetic memory, is they don't have any mechanical parts. So that's the nice thing about flash memory. Okay, so it's basically a type of EEPROM. Okay, so the bits are stored in an electronic chip. Okay, and they can be programmed and erased electronically or electrically. No, there are no mechanical parts. It's non-volatile storage, which means that you can store things permanently there, but there are some caveats. Okay? The main difference is that if you erase things in flash memory, there are only so many times you can erase before you can no longer use that location in flash memory. Okay, so I'm out of time right now. Next class we'll come back and we'll talk about flash memory and then file system, and then maybe we'll be able to do that in the first half of the lecture. Second half of the lecture we'll start talking in terms of what kind of projects you can do. I'll post a list of projects on Moodle that so that will get you started thinking about what kind of projects you can do here.